Okay, so welcome everybody. My name is Camilo Silva, and I will teach you this time in a virtual way the course Nonlinear Dynamics and Chaos. So this is a little silly joke, but I like. Okay, maybe it's not funny anymore, but I just realize I have a strong accent when I'm talking in English, and sometimes people think that I'm talking about cows instead of cows, chaos. So please don't think about chaos when I'm talking about chaos. This is just said, so we're happy with this. We will be based on the book of Strogatz, Nonlinear Dynamics and Chaos with applications to physics, biology, chemistry, and engineering. You have this on the library here in the faculty. You can also uh, have it digital in a digital format, okay, a PDF. So please, it's a good idea to have this with you so that you can accompany your understanding and the slides and the videos during the course. Okay, so it is more than fair that you actually know who is talking to you, which is me, Camilo Silva. Okay, so I'm being right now. I'm a lecturer and associate research associate at the department already for 7 years, 8 years, more or less. And I've been teaching this course already for 2 years, 2 years and a half. And has been also well received for from students. I'm very happy with this. Of course, is because the structure of the course is basically based on an amazing book, as I showed you in the slide of Strogatz, which is very insightful to understand maybe complex phenomenon in a very simple way, and that's why I like it very much. So I wanted to let you know first why studying nonlinear dynamics and chaos. What is the purpose of it? And this is something that I actually discovered after my PhD. When I was doing my PhD, I was amazed, or I am still amazed by computational fluid dynamics. It's beautiful. Maybe you know you have worked with it before, because you are able to understand in a very detailed way a given partial differential equation. Imagine you have an Navier-Stokes equations. When you may have even reactions. You can have a flame. You have all the reactants being mixed. You have maybe some acoustic waves being created by the flame. You have this insightful thing. And sometimes you spend, for example, 5 6 days to have maybe in making these huge computations to have maybe 3 seconds of physical time, so it's very expensive. And in some situations you may have, like, imagine you put a probe in your CFD domain to measure pressure, and then you realize that the pressure at a given point start to fluctuate and doing crazy things like waving, going back again to a stable pressure, and then again starting to move. How do you understand this? Uh-huh. And I've realized that a powerful method to understand actually complex systems is just reduce order models. This is a very fantastic way to understand that in this case you have a so-called thermoacoustic instability happening. How these low order models are created? So low order models means I will capture the essence of a system by a reduced model, and you can think a reduced order model to be, for example, a ODE, an ordinary differential equation of systems describing this complex domain. And something that amazes me the most is that these ODEs can be actually very simple sometimes, still non-linear, because non-linearity is important to maintain a lot of richness in the physics you are describing. But as long as you have this ODE being nonlinear, you can actually describe a lot of dynamics happening, and sometimes even so complex dynamics that is chaotic. So sometimes when chaos was discovered, we will just discuss it today. You had a super tiny system, that for certain conditions, some parameter arrangement, you would produce oscillations that will never repeat and that you cannot predict. And this is something that is actually intrinsic of chaos. So every complexity or much of complex systems can be actually reduced to a ordinary differential equation of a system of equations to be mathematically more simple, but still the complexity is there and you can understand it in an easier way. And this is why one of the reasons I like now this world of nonlinear dynamics and chaos. Now, when you have these tools as an engineer, these reduced order models or this ODE understanding of the systems, and the PDE or the partial differential equations CFD world in your mind, let me tell you that you have powerful tools to confront your professional career, your professional life. Okay, and something that to be maybe remember is that most of the time, I would say in my experience, any partial differential equation, if you are smart enough or you have the appropriate tools, you will be able to reduce it all the time to a system of ODEs. And this trajectory is something that maybe you will learn not in this course, but it's something that you should aware that exists, and that all the things you will learn in this course are already thought to be or to be applicable in very realistic complex systems. Okay, so I will say goodbye right now. You will not see my face anymore, maybe from time to time, but let's start now with the introduction of this course. Okay, so ladies and gentlemen, we are humans, and as humans we have always wanted to look at the stars and understand our future, to be able to predict, to be able to really understand nature. And that's why sometimes we have based our beliefs in mythology, religion, and from already some centuries from actual science. And when looking at science and trying to understand some rules to understand nature, our hope was to be able to understand where thunders were coming from. If it was not God, what was this? Or being able to understand this somehow a strange fluid that is pictured in terms of flames. So even when I was starting my career, for me this was just far away from reality. How are you able to really simulate these kind of things and be even close to make some predictions? But of course, we cannot start from this. Right now, there are conservation laws that allows us to be able to predict this kind of dynamics. However, at the beginning, we were in a more, let's say, simple world. So at the beginning, we wanted just to understand what in that moment seemed to be a very simple problem, like a pendulum. So based on dynamics, that is somehow this foundation is given to Newton, we were able to really, from in a structural way of thinking, to understand the system, in this case the pendulum or the two-body problem, and being able to really know what is going to happen. So to be somehow predictive, to have a deterministic system, and based on those equations to know what is going to happen. And that was, this is great. We see here the example of two-body problem, so the motion, that how they interact when they are actually rotating. And these equations, coming from differential equations, could be solved. Now that was very nice because you could predict this kind of interaction between these bodies. But what happened when the equations were imposed in a three-body problem? That was actually, let's say, the end of the road. Because yeah, you have the actual expression, mathematical expression of the problem, but nobody was able to solve it. In that moment there were no computers, so you have to do it either analytically or that's all. So you cannot just solve it. And that actually was a very critical problem. In the book of Strogatz, I like a sentence he says is, nonlinear systems are the norm in nature. And actually linear systems are the aberrations, which means that most of the time you don't find linear systems in nature. But anyway, if you wanted to have at least a solution for your system, the idea was, okay, let's linearize it at least. So at least we linearize it and we get a part of the answer. And let's see it with this example. I don't know if you recognize this equation is straightforward. Maybe some of you do, some of you do not, doesn't matter. Is the equation of a pendulum, the motion of a pendulum. And this equation already, we'll discuss it also next class, is not straightforward to be solved analytically. So most of the time what you think is, okay, so we just apply linearization. When we have the linearized system of equations, okay, in this case there are two first order differential equations, you will see, then we will be able to have an answer. And this is what we obtain. So we have here the linearized system, so we have the linear dynamics of the pendulum, and this is what we describe. So the pendulum is moving from left to right, and this is the corresponding phase diagram. This is something we will learn during the course. Okay, and that's all. Now let's see what we lost when we actually linearize the system of equations. In this case, this is the problem we already had before, but now imagine the rest of the picture. So the rest of the big picture, the same system of equations, now that is the entire equation, so it is still in this case is nonlinear. We are actually predicting situations like, this is frozen here, situations when you have a strong deceleration of the pendulum when arriving to the other equilibrium point, which is here at the top. Okay, and this is something that is not described by the linearized pendulum equation. Also, you have situations in which you maybe have a strong initial condition, then the pendulum is whirling all over the top and continues without stopping in the same direction forever, because in this case you see we don't have dissipation, so this system will turn like this forever. This is also described in here, in here, and in here, and in here. but the face portraits. Again, this is something we will see in the class. So the main message is that when we linearize, we have this portion, but when we comprehend, when we have the entire equation, which is just a little term here, which is makes the equation nonlinear, we recover the whole picture. And that's why it's not always a good idea to linearize a system to obtain a solution. Okay? It's sometimes better to maintain the whole complexity of the problem. Okay, but you may be wondering, I just said that sometimes it's not possible to solve the equation. Well, that was 100 years ago. Sometimes we have a numerical solution as well. But there is something in addition to that. There is still a pictogrammic way of understanding differential equations, and this is actually what Strogatz proposed, and this is what we actually do in this class. So we gain a lot by qualitatively understanding such equations. Actually, sometimes you may think, yeah, okay, but why to have it qualitatively if we can have just a code simulated numerically and we have it already done? Okay, sure, you can have it. But something interesting in the qualitative understanding is that you already obtain in your mind like the overall picture in terms of how a parameter affects my system. What happens if I change this parameter? What will happen to the solution at infinity? Or what are the equilibrium points if I change two parameters? These kind of situations, you cannot actually obtain it all the time from a numerical simulation. Sometimes you need like radiography of the ODE you are actually studying, and this is actually obtained by means of pictograms, or in other words, by means of phase diagrams. This is the drawing way of understanding physics, and this is nothing but already suggested in the work of Henri Poincaré. He says, it is through science that we prove, but through intuition that we discover. This means that intuition is important for creativity, and intuition is just images in our minds, and this is what actually is important to get. There are genius, okay, people that is just born geniuses and then just do amazing stuff because they have this intuitive capability from the beginning. But the other human beings, as maybe some of you or me, we need help to gather these intuitive capabilities, and nothing better than pictograms to have this intuition. Here there is something else to say in terms of determinism. So when scientists were able to describe a system by a differential equation, they knew that a given input will produce an output, and if you have the same input, you will have the same output, and there you will be able to see if I have an output at time 1, at time 2, at time n. So somehow you will be able to determine the future based on the model you were actually using. And that was the concept of determinism. If I have a system that is deterministic, and if I happen to discover the model for that system, I will know everything about that system. I will be able to determine completely all its dynamic properties in the past, present, and future. Okay? And that was the idea of determinism. But something happened when computers actually came into the picture. That was around 1950s. So here we say computers revolutionized the understanding of dynamics. What does it mean? Well, it means that people were able to rely on computers to solve the differential equations and to know the answers. And yeah, most of the equations at the beginning, they were classical deterministic equations. So you kept the deterministic paradigm in your minds. But then this guy, you maybe already have heard about him, Lorentz, show up. And with Lorentz, he was trying to understand weather. So he was trying to describe in a very tiny system of differential equations how weather behaved. Okay, so he was using some models. He has this idea of having the computer work during the day. Then he had to go home at some point, and then he come back the next day, and he started from the solution of the previous day, the last solution of the previous day, and so on. And for at some point he wanted to repeat the procedure to verify something, I don't know, and I realized that the answer was completely different. And he tried again, and it was also different again. So the first thing he was, oh, these computers are actually still far away from being reliable. Okay, so of course the first idea is to find like the guilty, who is guilty of these crappy computations. But he was smarter than just looking at of who is guilty or not to understand what's going on. At some point he realized that just by the fact of cutting decimals in the last solution, so in this solution that he will use the next day for the starting the computations, cutting the decimals for that solution will completely determine how the solutions will be. So he realized already that the solutions were sensitive, very sensitive to a given initial condition. And he was able to write it down and put it in a paper. Okay, this paper, this very famous paper right now, was completely hidden for 10-15 years until other people like him discover again the same kind of properties of some mathematical systems, mathematical models that have this strong dependence to initial conditions. Actually, you may think that this happened to Lorentz because he was using not 3, 4 decimals instead of 10, 12. Well, indeed, that was the reason, but that doesn't mean that it does not happen today when simulations sometimes exhibit solutions with 16, 32 decimals. The most classical example is just systems described by the Navier-Stokes equations. So the Navier-Stokes equations, before a given threshold, a given Reynolds, they behave like deterministic systems, and these are the flows they describe before certain Reynolds numbers are the so-called laminar flows. After a given Reynolds number, your flow becomes turbulent. In mathematical terms, it means that the equations become chaotic, actually. So in this case, we can make a relation between chaos and turbulence. Okay, I'm saying that there are people that says that turbulence is not strictly chaos, that you cannot demonstrate it, but at least from the point of view of the equations, you can see that a big simulation that is describing a turbulent system. Imagine you have 10 snapshots during your simulation, and then you do the simulation the day after, and you capture the same snapshots, also at the same times. You will compare the snapshots, and they will be completely different. This happened already when I was in my PhD 10 years ago to a student there, when he was trying to reproduce the instantaneous fields of a channel flow, and he couldn't, and everyone was like desperate because everyone was thinking that the code was completely garbage, but it was not the case. The case was just the chaotic inherence property of Navier-Stokes equations in the turbulent regime. So, just as a side note, it doesn't make sense at all to compare instantaneous solutions in turbulent flows because of this intrinsic chaotic behavior, sensitivity to a given change. So in this case, for example, what was the reason that the solutions changed from one computation to another computation another day? Because sometimes you know, the supercomputers, you can use many processors. You can have 128, 512. So some days he had availability of a lot of processors. He used all of them. Some days he needed to use half of the processors because the others were somehow already taken. And the fact of changing the number of processors changed the way in which these computations are done. So you sum from the node to the left, you sum the node to the right, and you combine the result. Or if you have more processors, you do the computations in a different way. And because of the chaotic not nature of the system, in a given moment you will have the 16 decimal being different in your solution. And this little error will propagate downstream in time until you actually split completely the solutions and after a certain time horizon, and then you have these like these two different ways in which the solutions go. And this is also a property of chaos. This is just an example I wanted to tell you. So I was reading a book of chaos, and it was funny. The author was telling that pendulums were most of them were in museums because they were, yeah, okay, it's a pendulum. I mean, nothing special. And then people, or say respected physicists, they were studying like maybe turbulence or even quantum mechanics, and of course nonlinear dynamics was too primitive to be of interest for them. When chaos appeared and they realized that pendulum can actually show chaotic behavior, then a lot of attention was taken back, and pendulums were taken out from the museums, and they were used again for actually deep mathematical studies and physics studies. This is an example of the double pendulum that I want to show you here. So before starting, I want you to be aware of these initial conditions. Okay, so there is a shift in this initial condition, and you will follow the trajectory. Okay, let me show you. I will put play. So at the beginning, the initial condition was just a little different in here and in here, and you will saw that at the very beginning the oscillations were actually very similar. You go there. Okay, but little by little they deviate, and they become completely different. And this is already, so this complex dynamics is given just by a simple pendulum. I mean double pendulum. So when you go now in YouTube and you look chaotic systems, or even in Instagram, you have this page, you follow these pages of science. There are a lot of different kind of little like toy experiments to show chaotic behaviors. That's pretty interesting actually. And now let's go back to the Lorentz system. Okay, when we were talking about Lorentz, he was using a three-dimensional ordinary differential equation, so three differential equations. And in here, we just see the corresponding phase portraits. So this is supposed to be a three-dimensional image. And every line is like a path that a given particle follows in time. So you will see that this particle is moving along these paths, but these paths never repeat, and you will go like this forever. Okay, so they will never repeat, but they will not go away. This is the so-called butterfly attractor, and people already put in the pop culture of as a butterfly effect. So this is the classical example that a little perturbation created by a butterfly in the Amazonas will create a storm in Australia. So this is already the idea of the butterfly effect. A little change will produce a large change somewhere else. But basically, I think the name butterfly also comes from the fact that this like attractor, what is called a strange attractor, has the look of a butterfly. And this is a nice way of showing the dependence of initial conditions. So in here, imagine you have a lot of different points next to each other. And if the system was non-chaotic, all particles will remain in the same position and they will move, and they will remain like next to each other forever. But this is not what happens in reality for a chaotic system. You will see that the points in here, after a certain time, now they are spread, but they are still somehow following a trajectory. After more time, they are kind of spread all over the attractor, and finally, after a certain time, every single point is far apart, and they are actually all over the place in the attractor. So it's interesting to see that one point, or let's say a collection of points in this region, after a certain time, they just go in completely different paths, and that's why you have like a feel, like sense of the points in the attractor. There is another way of looking at this problem, and I like it very much. So it's like considering a feedback loop problem. When you have an initial condition, the system, the response, and the response get fed again into the input. So we can describe this system just, for example, we have the e plus 1 equal fx I, and then the output is gonna be put in fx I plus 1 x I plus 2 and so on. Okay, so in your numerical method classes, you may think this as a fixed point algorithm already. Okay, and when you look at a plot, for example, here the number of iterations, and here the value of x, you may have a situation when you have actually convergence, which means that there is a fixed point, and then after some oscillations, maybe, who knows, or maybe no, you will reach the fixed point. So this is a possible outcome of a feedback loop problem. The opposite can also happen. The opposite, it means that you have a divergent problem. So instead of having something that is converging to a given fixed point, you have something that is getting away from that fixed point. Okay, so you starting here. This is your initial condition, but then you just wait. Okay, so these are actually two possible outcomes of the system, and this is something that we think is the case for most of the case for all the time. Now my question is, there are additional two possibilities as outcomes. Okay, so I want you to tell me what is or just think a minute. Okay, so another outcome that can happen is that the solution oscillates. So you may have an initial condition, then you go in here, then goes back, come here, goes back, here goes back, here goes back, and so on. So you have an oscillatory, it doesn't converge, but it doesn't diverge. So this is another possibility. And another possibility, that is the one that is more of interest for us right now, is the one that a chaotic system produces. So in that case, you will have oscillations that doesn't repeat ever, and they remain bounded as well. So this is a possible outcome of a chaotic system. Now, imagine that you want to plot this system of equations and now allow these variables x to be complex. So in that sense, you will see something like a real part, imaginary part, and at every single iteration, you will put a point in the complex plane. Okay, so if you have a deterministic system, if you have a system that is convergent, what do you expect? You expect that it's gonna be the same point all the time. Okay, like this, because it's convergence. Or you can have a solution that is basically repeating again all the time, like this oscillatory behavior we saw. But now what happens when we have a chaotic system? So you may think, so the first idea is, okay, we will have just points all over the place, and they remain somehow bounded. Okay, this is what actually happens, but in a much more beautiful way, as we will see it. Ladies and gentlemen, we are talking about fractals. So when we do this kind of exercise with chaotic systems, we obtain nothing but fractals. And depending on this f function I just showed you before, you will obtain different kind of fractals. You can have the Mandelbrot set, you can have the Fern fractal, and this is mesmerizing. I mean, how this is very close to nature in this sense. And this is when you start thinking, oh my god, this is chaos, which is supposed to be disorder, but chaos is actually organized. It's like the order of disorder. Maybe nature works in this way. So nature doesn't know about conservation of mass, energy, and momentum. I mean, a molecule itself, but it just receive a given information and give it back. Receive information and give it back. And depending on how this molecule, this system is defined, you will create at the end a very complex system that can be, for example, a fern. Here is a different way of looking to a similar problem. So instead of having a function, you have just a set of rules. And if you repeat this set of rules, you can create also what is called the chaos game. So you have feelings of particles. You can look this in internet as well, and you will be able to construct very different kind of structures, which are fractal structures as well, depending on the number of the kind of rules you are actually imposing. Is it possible also to have these cellular automata? In this case, this is like a certain like a chaos game. I really encourage you to look this on the internet. It's like a chaos game, but now you have rules, but also you have like boundary conditions, so you have like rules for your neighbors, and this is a way of describing a much more complex system. So I think this is something related to the live game. So at some point you can extinguish the whole population of particles, or you have saturation. So there are different dynamic evolutions that are sometimes very hard to predict. Someone that I like a lot is the concept of the lattice-Boltzmann equations. So unfortunately, I haven't had time to work much on these lattice-Boltzmann equations, but they are based on the same concept, on rules that are repeated again and again and again and again, and based on these rules, you can actually describe very complex system of equations, like the wake produced by a bluff body. So this Kármán vortex street. So you can do this with classical computational fluid dynamics, with conservation of momentum and mass, but also you can do it with just repeating some rules that are just basically called lattice-Boltzmann equations. And as well, this has been shown to be much more like cheaper computationally talking. Right now, this is also possible for acoustic waves, and all these automobile manufacturers, they have their own lattice-Boltzmann solvers to model, for example, acoustic waves created by the wind, and a lot of aeroacoustics also influence in the design of the cars, and there has been greatly a lot of benefits coming from the lattice-Boltzmann paradigm. So is chaos with feedback? What we have seen since this feedback loop is just chaos with feedback. Is chaos with feedback the explanation of complexity in nature? Of order of nature? This is even a philosophical question, maybe, that is interesting, and maybe this is even the reason of evolution. Why not? Maybe a system that it was tiny, that was following certain number of rules and was having feedback, evolve into us, the human beings. So this is something to have in mind. Okay, this is just some thoughts I have. Okay, so let's talk now about the methodology of the course. So I like this picture as well. I just read it. I believe in intuition and inspiration. Imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world, stimulating progress, giving birth to evolution, it is, strictly speaking, a real factor in scientific research. So as I told you just in some slides before, there are geniuses like Albert Einstein that they are born with imagination. Most humans, they don't have this capability or just imagining complex things, experimental thoughts from nothing. So myself, I have acquired a lot of intuition and imagination thanks thanks for CFD, and also because I have entered this world of nonlinear dynamics. Imagination can be built, and this is what I want you to learn in this course. So this creativity, this imagination, the imaginative minds, they come from the moment in which you can actually picture images in your minds. And this is what we will do with face portraits. Okay, so we enter now the last part, so the 2 or 3 more slides. And I wanted just to remind you something that I just said at the very beginning, is the fact that we can actually have an ODE from PDEs depending on the technique we are using, some linear algebra from some kind of mathematical projections or some kind of non-similarity analysis. So it depends on the method you are working with. But something that you have to be, you have to have clear in your minds is what is an ODE and what is a PDE. And something that actually helped me a lot when I was getting into this world is imagining an ODE. So you know that ODE has one, or depends on one independent variable. So in this case, we will manipulate only equations that depend on time. Okay, so x, or let's call another quantity, let's call it, I don't know, phi. Phi depends on time only. So you can imagine this to be like when we call about the face portraits, like a particle moving in a face portrait. A PDE is, you have more independent dimensions. So in our world, let's say in fluid dynamics and physics, in continuous mechanics, so we have space, x, y, z, and then we have time, so we have 4 dimensions. So most of the time the PDEs will be based on these 4 dimensions. And again, you can shrink these 4 dimensions into one particle, so in an ODE, if you have the appropriate tools. Okay, so now we have a classical equation. I hope you haven't forgot. This is nothing but the pendulum equation we just saw before. So I want to introduce just in 2 slides the concept of face portrait. Anyway, we will see it in the next class. And the first thing that we want to do, okay, in the normal class, there are 2 guys that come and write this equation as 2 first-order differential equations. Right now, I mean, we don't have to do that. Then I will just show it straightforward. Just to remind you that we will use, when we talk about first-order differential equations, we are talking about 1 dimension. When we talk about second-order differential equations, like this in this case, we are talking about 2 dimensions because we have 2 different equations. Because we can express this as a 2 first-order differential equations. Okay? To have in mind. And each dimension has a given axis in the phase diagram. And this is what I want to show you in here. Then we have a dimension x1 and a dimension x2. For chaos, we will have a dimension x3 as well. Okay, so this is the final slide. I hope that you enjoyed this introductory class. We will see anyway on Thursday to discuss again the slides and to have some interaction and some talks. And please prepare all the questions you want to ask and we want to discuss. Okay, I would like this to be very alive, a live course. Okay, so have a nice day. Bye bye.